Okay. You want to do an example of first and second derivative test real quick? Okay. So let me go find an example. All right, here we go. So, question. Can we do first and second derivative test example? Do y'all just want me to give you an example when you try it? Or do you want me to work it with you with explanation, just work it so you can follow along? What do you want in this respect? With explanation. Okay. All right. So we're going to find all extrema on the interval from -2 to 1 of this function using the first and second derivative tests. All right, so I'm going to do this in two separate parts. First, I'm going to do the first derivative test. Then I'll go back and do the second derivative test. So the first derivative test, you're going to want f prime of x to change from less than 0 to greater than 0 for a minimum. Or you're going to want f prime of x to change from greater than 0 to less than 0 for a max. That's first derivative test. So, to take the derivative, we're going to need to use product rule, so I'm going to do first. The second involves chain rule, so I'm going to bring down the power. The power was 2, so I write that in front. I leave the guts alone for the first round. 2 minus 1 is just 1, and I don't need to write just the 1 power up here. Then I'm going to multiply by the derivative of the guts. The derivative of x minus 4 is just 1. Then I'm going to add the second. Hello. Alright, that was weird. I'm going to add the second. Hello, are we back? Okay, so I've got the second, and then the derivative of the first, the derivative of x plus 3 is just 1. Are you all with me on the derivative of that? Okay. So now what I'm going to do is I'm going to make my life easy by noticing each of these has an x minus 4 term that I can factor out. Yes, you could also multiply it out and then take the derivative, but I like living my life expediently and not taking my sweet time about things. So if I take out the x minus 4, then I'm left with 2 and the x plus 3, and just 1 x minus 4 left. So simplifying the inside, we've got this. So now what we're going to do is we were leaving this as f prime of x all the way up until here when we're saying that it's going to equal 0. And once we say that it equals 0, we're going to get critical points. Okay, and the difference, because I know I'm about to get this question asked, between critical points and stationary points are the x values for which f prime is equal to 0. Critical points occur when f prime is either equal to 0 or does not exist. Okay? So I'm going to take this. Yeah, TanV, if you want, you can enter it into your own graphing calculator. That's something that you can definitely do. But in all seriousness, are you talking about seeing critical points versus stationary points on a graph? Okay. So this is a generic example. Let's say I've got this, and a cusp, and another hump. And let me make this let's just start over. Okay, I want an up, a vertical tangent, a down, and a corner. Okay, so stationary points are here, here, and here. Those are stationary. Meanwhile, critical points, let me get the appropriate color. Critical points occur here, here at this vertical tangent, here when the slope is 0, here when the slope is 0, and here when we have a corner. Okay, critical points and stationary points have a relationship similar to that of squares and rectangles. All stationary points are also critical points, but not all critical points are stationary points. Does that clear stuff up for you, Tanvi? Okay. So the critical points that we get from solving for 0, we get x equals -2/3 and x equals 4. Those are our critical points. Now, just like Chad said, we're going to do a number line test. We're going to label our number line, and we're going to go from -2 to 1. Those are our boundaries. And we had -2/3 and 4. Now, between 2 and -2/3, this is a real nice number called -1. Between -2/3 and 4, there's this other really nice number called 0. But 4, that's outside of our interval, isn't it? So let me go ahead and fix myself before I wreck myself. So notice 4 is outside interval. So we don't care about it. Okay? So we just need to check -1 and 0. Now when we plug -1 in, yeah, we just abandon it off on the side of the road in a cardboard box and hope someone gives it a good home. If we put -1 in, we have -1 minus 4, that's going to be negative. Then we're going to have -3 plus 2, that's going to also be negative. So we're going to have a negative times a negative. That's a positive. If we put in 0, we're going to have -4 times 2, which is -8, which is negative. So we go from increasing, I'm going to get a highlighter. We go from increasing to decreasing. And then what we say is that since f prime changes from being greater than 0 to being less than 0, yes, there will be a max at negative 2/3. So to being less than 0, there is a relative max at x equals negative 2/3. That's it for the first derivative test. Now for the second derivative test, we're going to need critical values. Yeah, on the test, I need to see some sort of justification, like what is inside this gold box. If you don't have some sort of equivalent to what is inside this gold box all the way, so you need to have everything inside this box. Okay? If you just tell me that there's a relative max at negative 2/3, that will be wrong / incomplete. Yeah. Now, the second derivative test for critical values, yes, you can use increasing and decreasing instead of greater than 0 or less than 0. So the second derivative test for critical values, so the second derivative test for critical values of f of x, if f double prime of x is greater than 0, there is a relative minimum. If f double prime of x is less than 0, there is a relative maximum. And if f double prime of x equals 0, it is inconclusive. You have to use the first derivative test. Use the first derivative test. Okay? So just to go ahead and pull the original function down, Alright, so we have this. And I'm going to grab this here. Excuse me. There we go. So we had f prime of x equaled the x minus 4 and the 3x plus 2. Chad, do you still need me to scroll up? Like, do you need to see the second derivative part? Did I say Chad or Matt? I meant Chad. Chad, are you good or do you need me to scroll up further? Okay. So... Alright. We're here. And my brain farted because it's past my bedtime. Second derivative. There we go. F double prime of x. First derivative, or first d second plus second d first. Now I don't see anything that I can factor out, so I'm just going to simplify and expand. 3x minus 12 plus 3x plus 2. I've got 6x minus 10. I'm going to take out a 2. 3x minus 5. All of this has been f double prime of x. And we're not setting this equal to 0 because we're not trying to find points of inflection. We're going to now plug in our critical points. So I'm going to plug in negative 2/3. Yeah, I had a good time with Rhyme, and then people actually needed some help, and I'm glad that this is working out. Because this is a lot more comfortable than after-school tutoring, and it's probably a lot more comfortable for y'all too. So f double prime of negative 2/3 is negative 14, which is, and I'm going to put this in a different color, that's less than 0. So we are concave down. Yeah, keep the profanity down. That'd be good. I'm trying my best not to swear, so... Uh-huh. Sure you did. Sure you did. So since this is concave down, we're going to have a relative max. It'll be okay. I forgive you. I won't ban you just yet. And we won't need to test the 4 because it's outside of the interval. right? Because our interval was what, -2 to 1? Yes. So our final answer is just this. And that's for the second derivative test. Y'all feel okay with that? Oh, if it were to ask for the point. So if it asks for the point, we now know that this is a relative max because we've checked it both ways. So if it asks for the point, all you do is you go to the original function and you put in that value. And in this case, we're going to have, there it is, the -2/3 plus 3 and the -2/3 minus 4 squared. And we'll have to solve this out to get the point. So we would have -2 plus 9 over 3 and -2 minus 12 over 3 squared. So 7 over 3, -14 over 3 squared. Okay, so Envy, I see your question about going over comparing the graphs of derivatives to regular graphs. And I will do that as soon as I finish this and go back up to the linearity for Thompson real quick. Okay, so we're going to have 7, and I'm a bad math person. I don't know what 14 times 14 is. 196. So we have 196. However, I do know what 3 cubed is, and that's 27. What kind of coffee do I drink, Chad? I just typically get like store coffee and add the International Delight Irish creamer to it. That's my favorite flavor. Yeah, I will need some tomorrow, and I'm all out of the creamer, so I'm gonna be in a rough state unless I go and get a coffee from a drive-thru. Yeah, can be. So 7 times 6 is 42. Is my brain working? Yeah. And 9 times 7 is 63, so 7, 6, and then that is 13. So 1372 over 27. That doesn't simplify, does it? Oh, well, if you're gonna get me something from Dunkin' or Starbucks, it depends on where you're going. I can give you my order for either. Dunkin'? Yeah, give me a second. I'll give it to you. So this would be the final point, right? So this, we would know, is a relative max. And to figure out if it is an absolute max or not, we'd need to test the endpoints. So we need to test f of -2, and we need to test f of 1. So f of negative 2 is negative 2 plus 3. Negative 2 minus 4 squared. These are numbers I feel like I can work with. 1 and negative 6 squared, so 36. F of 1 is 1 plus 3 and 1 minus 4 squared. 4 and negative 3 squared is 4 and 9, which is also 36. So after we've done this, now we can say that negative 2/3 50.8 is an absolute max. And this, I'm going to make a note, testing endpoints. We do this because of extreme value theorem. Okay, extreme value theorem says that there's going to be at least one minimum and then at least one maximum. But outside of that, we use our first and second derivative test to determine the additional ones. And then we test the endpoints to figure out the absolutes. If you just do the first or second, then you just know that they're relatives. Chad, what if they did not equal? Well, like if one of them was like 37 instead of 36? Then it would still like not matter, because 36 and 37 are both lower than 50.8. 50.8 is the highest y value that we achieve. Now, if one of them was 90, then we wouldn't have an absolute max at negative 2/3 50.8. So we would have just a relative max. The extreme value theorem changes our critical point, stationary point areas from being relative to the maximum, or to the absolute. Okay, Thompson, you're still in here, right? Okay. The linear stuff that we did for local linearity was way up at the beginning. It was one of the first things we did. All right. And so I think this was Lily who asked this question. How do we know when a linear approximation is an over or underestimate? My answer depends on the function's concavity at the point. Okay. The yellow lines in here are the tangent lines at the point, and then the points that are on the tangent line there are points that we would get from approximations. You'll notice that the points are over the original curve if the curve is concave down, so it turns into an over approximation. And then the points are under the curve if it is concave up, so it's an under approximation. Yes, I did go over Rolle's theorem. It's inside this document that I will be uploading to eCampus before I go to bed. So you'll at least be able to see the example and the work solution on Rolle's theorem. Up is a cup and down is a frown, yes. And if you were to put your pencil on a concave up, every point on the pencil would be underneath the cup, And if it's a frown, every point on that line would be above the frown. That's how you get your over and under. Okay. And yeah, that's it for over and under approximation. From the example in class, this is that. So that little message that Chad gave you, he capitalized the U's in particular because the U in up does correspond with the U in under approximation. So if that helps you study it or keep it in mind, then that's something that I would definitely recommend you keep inside your brain. Oh no. Can you not do that? Whew, good. All right. No. Stop. Function analysis would appear the most frequently on the test. Ooh, what did I not go over in here? Well, this is the Rolle's theorem stuff. Yeah, I didn't go over mean value theorem. No, Chad, I covered extreme value theorem. That was me explaining the endpoints and why we test them. Yeah, I can go to that. Alright, so comparing graphs. Actually, instead of doing it on this, I'm going to see if I can't get the GeoGebra software to work. What do you mean write out a response for the approximations? For the approximations, you just have to tell me the approximate location of the point that I tell you to find.